Hey, hello, good morning, everyone. I'm so sorry for the delay. So today we will talk about exam two, and then we will talk about the hints to the solution. So some of them, I still hope that you can finish it by yourself. Think about it using the hints given today. So let's start. So there are 5 questions here. So the first question is, we are given a certain random variable x, and then we know that the moment generating function, which is a function of t, for this random variable x, looks like the following. And our question asks us to find. So first of all, let's try to find another easy to understand random variable such that the moment generating function is the same. So let's design a certain random variable y with the same MGF. So if we analyze this MGF, it is the product of 3 terms, and for each term it is regular. It is always looking like there is some constant multiplied by e to the power some other constant to the power t, and then the constant coefficients here adds up to 1 in each cases. So in that case, we can view that this is actually a moment generating function for some random variable. This is also the same, and this is also the same. So in particular, we will see that this is a product of 3 moment generating function. So in that case, we can design a certain random variable, which is the sum of 3 independent random variable. So that the first one has this as the moment generating function, the second one has this as the moment generating function, and the third has this as the moment generating function. So we are going to design a random variable y, but this y is going to be the sum of 3 independent random variables, y1, y2, y3. And then for y1, we set the probability that it is equal to 0 with 0.4, it's equal to 1 with 0.1, and then it is equal to 5 with 0.5. So this is the first random variable, y1. And then y2 is there is a chance of 0.4 for its value to be 2, and a chance of 0.6 for its value to be 3. Is that okay? And similarly, for y3, it is like this. So by setting up this, we know the fact that since x and y, they have exactly the same moment generating function, then their probability distribution are going to be the same. So the expected value of x is going to be the expected value of y. So by linearity of expectation, it is the expected value of y1 plus that of y2 plus that of y3. So we can compute it, and then if my calculation is correct, then this is like 2.6, and then this is also 2.6, and then this is also 2.6. So we add them up, so we get 7.8. Okay, now the second question is, we want to find out what is the chance that x is greater than or equal to 4. So x and y are having the same MGF, so x is greater than or equal to 4 happens. We can compute the corresponding chance of y to be greater than or equal to 4. But recall that y is the sum of the 3 smaller random variables, and then for y2 and y3, it is always greater than or equal to 2. It has value either 2 or 3, right? So in that case, no matter what happens, the sum of the 3 y1, y2, y3, these 3 independent random variables will always have value greater than or equal to 4. So the chance of y greater than or equal to 4 is always happening, so it is equal to 1. Okay, so we can do this easily. Okay, for question 2, we have x and y. They are independent Poisson random variables, and then x has parameter 1 and y has parameter 2. And we let z to be x plus y, and then we want to find out what is the probability of z is equal to 1. So you can compute this by brute force. So for z to be equal to 1, there are 2 cases. Either x is 0, y is 1, or x is 1, y is 0. So you can add these up, and then because they are independent, so you can compute it easily. But then for this question, we actually want you to recall that sum of independent Poisson is actually a Poisson. So we know that Z is a Poisson random variable as well, and it will have parameter 3. So simply, the answer for this one is, what is the chance that a Poisson random variable with parameter 3 will be equal to 1? So it is going to be the parameter lambda to the power 1 multiplied with 1 to the power 1. Sorry, lambda to the power 1 multiplied by e to the power minus lambda divided by 1 factorial. So we get this as the result. So you can check this. So basically, the answer here should be the chance for a certain Poisson random variable with parameter 3 whose value is equal to 1. Okay, so this is going to be like this. Now the third question talks about the scenario in a supermarket, and then we have n customers and n queues. We assume that the queues are all empty at the beginning, and then each customer picks a queue uniformly at random. And after they have selected the queue, then the queue will start serving the customers. So each queue serves exactly one customer in a round. So we want to find out what is the expected number of customers served in the first round, and also what is the expected number of customers served in the second round. Now, for this one, there are many ways to compute it, but then I find this to be easy. So we just find out how many empty queues are there in the first round. So for all the non-empty queues, they will be serving customer. So by finding out the number of empty queues and deduct it from n, then we get the result. So n minus the expected number of empty queues. So the expected number of empty queue is equal to, so 1 minus 1 over n to the power n is the, let me see. Did I make a mistake here? Let me see. 1 minus 1 over n to the power n is the probability that for a certain, so here it should be, I think I have made a mistake here. So I should have an n here as well. So this is the probability that a particular queue is empty, right? Because for a certain queue to be empty, we need all the customers to be not choosing this queue. So the expected number of empty queue would be n multiplied by this one. So it is like this. Okay. So we get the result. Yeah, please double check for me whether it is correct or wrong. Okay. So we can compute things like this. The chance, yeah, something like this. Okay, good. Okay, and then for the next part, we also want to find out what is the expected number of customers served in the second round. So we are going to do the same thing here, except that not just empty queues should be deducted, we should also rule out all the queues that has exactly one customer, because for those queues, they are not going to serve any customer in the second round. So to find out the value, we find out what is the probability that a certain queue has exactly one customer initially. So for this to happen, among all the n customers, we need to pick one of them to come. So there are n cases, and then for each case, there is a chance of 1 over n for that customer to come, and then we require all the remaining customers not coming. So in that case, the answer will be the previous answer minus n times this value, because this is going to give us the expected number of queues that has exactly one customer. Is that okay? So this is question 3. So we don't require you to do what? Some of you might have used a Poisson random variable probability here, but it is not entirely correct. It is because for this one, we have the exact bound. We are not asking you for the approximate value. Although it is, for instance, this is really, really close to e to the power minus 1, but then it's not the same. So we are not asking an approximate bound. So the correct answer should always be just in terms of this n. Okay, this is question 3b. Now for question 4, the question here is very, very similar to homework 4 question 4. So you can go back and check. So there are just a few lines to modify, and then you can get a new result using the fact that for a certain using the new fact of Poisson random variable. So you can work it out by yourself. Now I want to spend some time on question 5. Actually, question 5 is the guided question. So let me see. So this is exam 2, right? Perhaps let me find out exam 2. So this is exam 2 question 5. So let's read the question together. So question 5, we are going to modify the balls and bean process so that we are, let's say we have exactly n beans labeled from 0, 1, 2, 3 up to n minus 1. And then there are k players where k is a factor of n. So we can divide n properly with k. And then we have k to be of the order of log n, theta of log n actually. And then each player chooses a location randomly, and then they place one ball in each of the bin from the location L, and then the next location L plus 1, and then the next location L plus 2, and so on and so forth. So we are taking modulo here. And then we want to find out the bound for the maximum load. We want to show that the maximum load is of this order with probability approaches 1 as n tends to infinity. Okay, so for this question, we can view this in the following way. So this is just a different interpretation of the same question. So let's see. So we can assume that there are n balls and n beans initially, and then the bins are arranged in a circle. Okay, and then what we are going to do here is we are going to distribute the balls into the bins, but then we are not going to distribute them one by one. We are going to distribute them in k rounds. They are k players, so we are distributing them in k rounds, and then k is of theta of log n. Is that okay? And then each round we will put the balls into n over k contiguous bins. Okay, so here, so let me change. Okay, so here we are going to put one ball. Okay, so this is exactly what is happening. Okay, and then what we are going to show here is, so the value, the magic value log n over log n is actually coming from log k over log k, because sorry, did I make a mistake here? So it is like a log n over log n. Okay, so this is, we want to show that the maximum load is of this order of log k over log k with probability close to 1 as n tends to infinity. So this is what we want to show. And then let's take a look of the hints. Okay, so we have the hints here. So the hints is here. So the hint first says that, okay, we are going to select k bins evenly as representative. So originally there are n bins around a circle. So we are going to select the one bin and then skip n over k, and then the next bin and then skip n over k, and so on and so forth. So in the end, we have exactly k bins selected, and then they are placed evenly. Okay, we want to show that the scenario of this case is similar to some balls and bin models with k bins. Now, what does that mean? Okay, let's use this figure to help us. So suppose that these are the k bins that we have selected. Now recall what? Recall that each round we are throwing n over k balls into what? Into n over k contiguous bins. So what does that mean? So each round there will be exactly one of these representative bins to have one ball coming. Exactly one, because the distance for this is at least n over k. So if there is a ball here, there can't be any ball in the other bins. So we will see that the original setting, we are putting n over k balls into n over k contiguous bins, will be like we are putting one ball into one bin here. Is that okay? So each round in the original problem corresponds to putting one ball into this representative bin. So the problem here is we want to find out, okay, so the problem here is what? The problem here is this with the maximum load. See that in this problem, we have actually studied something like this before. It is like we are going to have k rounds, each round put one ball in one bin. So we have actually showed that high probability, okay, with high probability, if k is of the order of n, with high probability, the maximum load will not be greater than log k over log k. Okay, but here k is not of the order of n, so we need to change the argument a little bit. So we will, as n tends to infinity, the probability of having maximum load in this setting to be greater than log k over log k is really small, or the maximum load of any of the bin here, of this representative bin here, will be like order of log k over log k with probability close to 1. Yeah, this time it is not with high probability because it is not polynomial dependent on n, but then we still can claim that it has probability close to 1 as n tends to infinity. But then there is still something missing because we are talking about the maximum load for these bins. Is that okay? But we are not talking about the maximum load of these original bins. Okay, but then they are still related. We will see that in order to create a maximum load for this one to be of a certain value L, for a certain value L, then we will see that any of the bins here cannot have a value of 2L. If a bin in the original setting has maximum load of 2L, it will immediately create a scenario for this one to have some bin with greater than L loads. Yeah, remember, we are distributing in contiguous region. So if a certain bin here receives L balls, then for this L balls, so if a certain bin here, let's say, let me draw it. So let me see. So notice that these are the bins that are the representative. So I'm omitting all the previous bins in the case. But let's say there is a bin here in the original setting. Let me use a different symbol for it. Sorry. Yeah, make it here. So let's say this is a certain bin that is in between these two bins with 2L. Then the balls here, either it means that this one plus this one has to have a load of at least 2L, because what are the balls coming from in this for this bin? So the balls, each of the ball that comes into this bin must either have a corresponding ball in this bin or a corresponding ball in this bin in the same round. So if there are many balls here, that means that either this one or this one will have at least half of the ball. Is that okay? So the relation of this one is needed so that we can now connect the two scenarios. This scenario is the original setting, and this scenario is the representative setting. So if the representative case cannot have a maximum load of L, that means that in the original setting, it cannot have a maximum load of 2L. Is that okay? So this is the idea of question 5. So I hope that by using the hints here, this is exactly what we are asking you to find out. This is a difficult question because you need to somehow convince yourself, or the tricky part here is that you need to convince yourself that the load in the representative case and the load in the original setting are related, and then make use of this relationship to deduce that the probability of having a very large load in the original case is going to be small. Okay, so let me see if you have any question. Yeah, something. It should be M customers and N queues. Am I? Oh, M customers and N. Did I make a mistake here? Oh, thanks a lot. Okay, so in that case, if it let me correct it. So thank you, thanks to Chin. So let me correct the question. Yeah, I my eyes have problems. So let me correct it. So can you all hear me clearly now? Yeah, if that's there, so that's all for today. So today I'm just preparing this exam 2 solution for you. So for next week, we will finish the whole course materials by giving you the answer of homework 5 and homework 6. Yeah. Yeah, that's all for today. Yeah. Let me know if you have any question. If not, yeah, let's meet again next week. I will make corrections and then send you the slides yes, after a moment. Okay, thanks all.